Okay. All right. So let's start the lecture. And recall what we were discussing yesterday in the last lecture. So that L over K is an extension of fields. And alpha is an algebraic element of L over K. Then just a second. So let alpha be an algebraic element of L over K. We have tried to express this notion of algebraicity in terms of evaluation maps. So consider a map from K bracket X to L, which takes a polynomial f of x to f of alpha. This map is denoted by E sub alpha. And if kernel of E alpha is non-trivial, then alpha is said to be algebraic over K. Otherwise, it is said to be transcendental. Then we have used the property that K bracket X is a PID. Therefore, every non-zero prime ideal is a maximal ideal. A maximal ideal. So if kernel of E alpha is non-zero, since you know that kernel of a ring homomorphism is always a prime ideal, it follows that kernel of E alpha is a maximal ideal. And we can ensure that this maximal ideal is generated by some polynomial M alpha, where M alpha is monic. Okay, and since kernel of E alpha is a prime ideal, it implies M alpha is also irreducible. So we have from this by the first isomorphism theorem of rings. So we have a ring homomorphism from R to S. Phi is a ring homomorphism, then R mod kernel of phi is isomorphic to the image of phi. Okay. So this map is simply constructed as follows: kernel of phi. So this map is the unique homomorphism which factors in this field, right? This is denoted by phi bar or phi tilde, depends on your choice. Okay, on your test, phi tilde, and yeah. So from this theorem, it follows that you have a map from K bracket X to L to K bracket X or M alpha. It's a ring homomorphism. Ring homomorphism denoted by E alpha tilde, like this. And this is the usual canonical map phi, which takes f of x to f of x plus this ideal M alpha. Okay. So from this, the next theorem says the following. So this map, the image of E alpha tilde is equal to A of alpha. Okay. Therefore, in particular, we see that A bracket X mod M alpha is isomorphic to A of alpha, and the isomorphism is explicit. It's not some arbitrary isomorphism. So we have an element f of x plus I is essential to f of alpha. So isomorphism is induced by E alpha. Okay. So what is the purpose of this theorem? Well, the elements of K alpha are fractions. Whatever that means, fractions. So it is of the form f of alpha or g of alpha. But elements of K bracket X mod M, this ring, are given in terms of polynomials. So the elements on the left hand side are of the form f of x plus I. On the right hand side, you have, instead of f, you can say A of alpha or B of alpha. Say alpha square plus alpha plus 2 or alpha cube plus 10 alpha square plus alpha to the power of 100 plus 4. No matter how complicated it looks, it always arises from a polynomial modulo I using this map. So that is so we have reduced, in a sense, we have understood the division of polynomials in terms of additions. So that is the importance of this theorem. That's all we need to show. So we have already seen that this map is certainly injective, and all we need to show is this map is the image of this map is K of alpha. That is all I need to show. Okay, so if you look at E alpha tilde, and if you take an element little k, which is little k, this is a constant. This is of the form k plus I is equal to k. Because it is a constant, you can't substitute anything. So it is a k. So the image of E alpha tilde contains k. And furthermore, E alpha tilde of x plus I is equal to alpha basically by substitution. This follows that alpha also belongs to the image of E alpha tilde. And therefore, since this is a field and E alpha tilde is a is an injective ring homomorphism, this is a field and this is sitting inside another field. It is injective, and therefore, whatever this field, the image of this contains K of alpha, the field generated by K and alpha. So remember the definition. So the field generated by A is the smallest field containing both A and K. So in particular, image of E alpha is also a field. So this also participates in this intersection, and therefore this is contained in this. So from this, you can easily see K of alpha is contained in M for any M which is participating in this intersection. In particular, this image, which is a field, because K, this is a field, and this is an injective map. So this image contains K of alpha. On the other hand, if the image of E alpha is nothing but E alpha tilde, so this is the image where f of x belongs to A bracket x. But by definition, this is equal to f of alpha. This is my image. This is equal to f of alpha. And therefore, f of alpha is already contained in K of alpha because it is a polynomial with coefficients in K in alpha. And therefore, this is also contained in K. It follows that the image of E alpha tilde is equal to K of alpha for the field generated by K and alpha. So the main importance of this theorem, as I said, is this, because you are understanding division in terms of addition and multiplication. So whenever you want to talk about an element of K alpha, all you can do is to talk about an appropriate corresponding element in this left-hand side. All right. Based on this, we have the following most important theorem, which characterizes algebraicity in terms of degrees. So let L over K be an extension, as usual, and let L alpha be an element of L. Then alpha is algebraic over K, if and only if the degree of the field generated by K and alpha over K is finite. So the most important part is if it is an if and only if statement. And it is also if this is algebraic, then the degree is given by the degree of the minimal polynomial. Recall the minimal polynomial is the unique monically reducible polynomial for which alpha is a root. Reducible polynomial over K. So this is an important theorem. In particular, if you know that L over K is a finite extension, that means its degree is finite, then you can easily see that for each and every element beta in L, you can say that beta is algebraic over K. You no need to find minimal polynomial of beta. Why? Because by the Tower law, so you can talk about a field K of beta, which is contained in L. Since L over K is finite, by the Tower law, it follows that K of beta over K is also finite. By this theorem, it follows that beta is algebraic over K. So this part is the important part, because you can talk about, you can decide whether an element is algebraic or not just by looking at this extension K of alpha over K and finding its degree. So just by looking at a number, you are able to say whether some element is algebraic or not. That means whether it satisfies some polynomial or not, which is, in my opinion, it's very important. Based on this, you will see several theorems which skips check finding some polynomial which alpha satisfies, but rather simply checks whether this is finite or not. So proof. So first, suppose the degree of k alpha over k is finite. Okay. Now consider the n plus 1 terms, 1 alpha, alpha square, alpha to the power of n. Okay. Now these are the elements of the vector space k of alpha, which is over k. Now so k of alpha considered as a vector space over k has dimension n. We know that if you take at least n plus 1 elements, the vector space of dimension n, they must be linearly independent, linearly dependent. So especially it may have one of the following two cases happen. Either alpha to the power of I is equal to alpha to the power of j for some I not equal to j. So two elements may be equal, in which case alpha satisfies x to the power of I minus x to the power of j, so that alpha is algebraic over k. Or else this is not true for any I and j, for any I not equal to j. And therefore, but since you know that this set is linearly dependent, there exists some constants k naught, k1 alpha, k2 alpha square, plus kn alpha to the power of n, where ki belongs to k and not all 0, which is equal to 0. So that is the definition of linearly dependence. So if you take the polynomial f of x is equal to k naught plus k1x plus k2x square plus kn x to the power of n, so you see that f of alpha is equal to 0. From this, you can say that E alpha is not 1 to 1, and therefore alpha is algebraic. So that is this part, this direction. So these directions. And now this part, suppose alpha is algebraic over k. And let m alpha be the minimal polynomial of alpha. So let us say of degree n. So if it is algebraic, there exists some more unique monic irreducible polynomial which alpha satisfies, and let us suppose that polynomial is again of this form, kn x to the power of n, where kn is equal to 1, right? Because that is the definition of minimal polynomial, and therefore it follows that so this is m alpha of alpha is equal to 0. So in particular, 1 alpha alpha square alpha to the power of n minus 1 is linearly independent. Because if this is not if this is linearly dependent, so you will find some constants such that the linear combination of this will be 0. I mean, some non-trivial linear combination of these elements is 0. But that would contradict the definition of minimal polynomial, because the minimal polynomial is at least degree n. And if you have a linear combination between these elements, non-trivial linear combination, that means the degree is at least n minus 1, contradicting the definition of minimal polynomial. And therefore, this must be linearly independent. Okay. So if you take so this is linearly independent, and we want to. So our aim is to show that k alpha over k is n, where n is the degree of the minimal polynomial. So we have exhibited a linearly independent subset of n elements. All we need to show is that this set also spans k of alpha, and here is where we use the theorem. So because if you want to write any general element of k of alpha, it looks like f of alpha over g of alpha. And then you have to struggle with this thing. Instead of doing that, you use the previous theorem, which says that k of alpha is isomorphic to uh, this ring. And therefore, if you pick any element in here, there exists some polynomial f of x plus I, which maps into beta, i.e., beta is equal to f of alpha, where f is some polynomial. So you see, this quotient, we actually gotten rid of this quotient, and we are able to speak in terms of polynomials. That is the main purpose of theorem, of the previous theorem. Okay. Now, f is some polynomial. So if f is some polynomial, then because k bracket x is a Euclidean domain, so if f of x is of the form m alpha times q of x plus r of x, m alpha of x times q of x r of x, where q and r are the coefficients by long division. By just following the definition of Euclidean domain, you get this. So from this, it follows that so beta is equal to f of alpha. So f of alpha is equal to m alpha alpha times. So the degree of r is strictly less than degree of m alpha. Q of alpha plus r of alpha. So this is 0, and therefore this is r of alpha. Since degree of r is strictly less than degree of m alpha, so r looks like k naught plus k1 alpha plus kn minus 1 alpha to the power of n minus 1. So that is to say beta can be written in terms of 1 alpha alpha to the power of n minus 1, which is precisely what you need to show, because you have a linearly independent set which also spans k of alpha. Therefore, so k of alpha considered as a vector space over k has dimension n. That is what we need to show here. And during this process, we have also exhibited the fact that n is nothing but the degree of the minimal polynomial. All right. Now, let us learn something more about algebraic extensions. So we use that result. This is corollary to the previous theorem. Okay, so let L over K be an extension, maybe infinite, doesn't matter. Let L alpha consists of L sub A consists of all those elements in L such that alpha is algebraic over K. Claim is L sub A over K. L sub A is a field extension. That means L sub A is a field. A stands for algebra. So well, the thing is this. So if you have these algebraic elements here, so it may happen that so you will have alpha to the power of 100, beta to the power of 1 million, 10 to the power of 6, and alpha to the power of 25 plus beta to the power of 60. So you have all sorts of this, all kinds of these elements. And it is it is impossible to find minimal polynomial for these kinds of elements and then show that L alpha is a field. Okay, so rather we use the previous theorem to show that the corresponding degrees are finite. Okay. So suppose alpha and beta are two elements in L, A is their algebraic. So beta is algebraic over K and alpha is algebraic over K. In particular, beta is algebraic over K of alpha. So you consider K of alpha beta, K of alpha K. So that is the extension I'm going to consider. Now beta is algebraic over K. Okay, beta is algebraic over K. In particular, beta is algebraic over K alpha also, because K of alpha contains K. So if beta satisfies some polynomial, let us say a naught plus k1x plus kt x to the power of t, where ki belongs to capital K, then of course this beta satisfies the same polynomial over k of alpha. So that shows that beta is algebraic. Okay, but so beta may satisfy, this may be the minimal polynomial over k, but this may not be the minimal polynomial over k alpha. This polynomial may split into two parts, split into split into two distinct polynomials, for which beta may be a root, for one of which beta may be a root. And therefore, this may not be the minimal polynomial over k alpha. But in order to decide whether something is algebraic, all we need to do is to exhibit one polynomial which that element satisfies. Okay, so beta is algebraic over k alpha. Now, this is k of alpha over beta. So note this, k of alpha beta is equal to k of alpha of beta. So both are the same. So if you add alpha and beta, and then take the field generated by both alpha and beta, this is the same thing as first take the field generated by k, alpha and k, and then take the field generated by beta and k of alpha. So both these gives the same set of fractions. This is easy to check. Now, if beta is algebraic over k alpha, this means k of alpha beta over k alpha is finite by the previous theorem. If something is algebraic over k, for any field, that extension field must be finite. Now, since alpha is algebraic over k of alpha over k is also finite. And therefore, k of alpha beta over k by tower law, which is the product of k of alpha of beta over k of alpha times k of alpha over k is also finite. Now look here, this is the important part. Now, so k of alpha beta is a field. In particular, this contains k of alpha plus beta, because alpha plus beta is already contained in k of alpha comma beta. And it also contains k of alpha beta. So you have a finite extension and you have a sub extension that must also be finite. This is again by the tower law. So you have m l over k, mk is equal to ml times lk. If these two are finite, this must be finite. If this is finite, these two are finite. And therefore, if you consider k of alpha beta and k of alpha plus beta, k of alpha beta over here, so this whole thing is finite and this is also finite. But by the previous theorem, if this is finite, alpha plus beta is algebraic over k. And similarly, alpha beta is algebraic over k. Therefore, we see that for any two elements, the sum and the product also belongs to n sub a. Okay. Now, in order to show that L sub A is a field, all we need to show is given an element, given some element alpha in L sub A, we need to exhibit that 1 over alpha also belongs to LA. So non-zero element. Okay. So since alpha is algebraic, suppose M alpha is the minimal polynomial, which looks like this: k of x plus little k of x to the power of n, because the minimal polynomial is monic. So this is the minimal polynomial which alpha satisfies. We will have k naught plus k1 alpha plus kn minus 1 alpha to the power of n minus 1 plus alpha to the power of n is equal to 0. So from this, you can easily see that, so you can take this k naught to the other side, minus k naught, and you take alpha common, you have k1 plus k2 alpha plus kn minus 1 alpha to the power of n minus 1 plus alpha to the power of n minus 1 is equal to minus k1. So from this, alpha times minus k1 by k0 minus k2 by k0 alpha plus minus 1 by k0 alpha to the power of n is equal to 1. So you have alpha times beta is equal to 1 for some beta. That means beta is the multiplicative inverse of alpha. Now you see all this is a linear combination of elements of 1 alpha up to the power of alpha to the power of n minus 1 with coefficients in k. Okay, so therefore it is already contained in so alpha inverse is algebraic over k. Why do you need that? So basically, what you did was, so you took this polynomial, this different polynomial here. I have shown that alpha inverse satisfies this. Oh, this is wrong, sir. This is wrong. So sorry. So this is my minimal polynomial for alpha. And in order to show that alpha inverse is also algebraic over LA, over K, but K alpha is a field, right? I don't know why you want to exhibit it all. So, okay, so LA, you take the K of alpha over K. Since K alpha is a field, alpha inverse also belongs to K of alpha. And therefore, if you consider the field generated by K of alpha inverse over K, so this must be finite because this is finite, and therefore alpha inverse is algebraic, therefore belongs to LA. That's sufficient. That is sufficient, I guess. Yeah. So this is wrong. So I tried to exhibit an inverse for alpha, but that's not the point of the story. All you need to show is that 1 over alpha satisfies some satisfies some polynomial, or you can easily see from this. So if you see f of alpha is equal to k naught plus k1 alpha plus kn minus 1 alpha to the power of n minus 1 plus alpha to the power of n. If you take alpha to the power of n common, we will have alpha to the power of n, k naught 1 over alpha to the power of n, k1 1 over alpha to the power of n minus 1, and so on, plus kn minus 1 1 over alpha plus 1. So f of alpha is equal to 0, but alpha to the power of n, because we are talking about field, so this is not 0, so this must be 0. So if you take the polynomial g of x is equal to k naught x to the power of n, k1 x to the power of n minus 1 plus kn minus 1 to the power of x plus 1. So you can easily see that 1 over alpha satisfies this polynomial, and therefore alpha is algebraic over k. In particular, it belongs to LA. But that is not necessary. You can easily see this from here. Okay, so if you take an extension L over K, no matter what that extension is, and we talk about L sub A consisting of all the elements, algebraic over K, so that gives you a field. In particular, if you take C over Q, then you have R is not algebraic over Q because it contains transcendental elements. So this is denoted by Q sub A or Q bar. Q sub A, Q alg, Q bar. So Q bar means algebraic. Okay? So this is the most important field, Q bar over Q. And number theory is all about understanding this extension, Galois, Q bar over Q. So we'll come to that later. So Now, uh, now what is the degree of the extension LA over K? If L over K is finite, of course L sub A over K is also finite. But if you want to show that Q bar over Q is finite. So how do you show that? How do you? This is infinite. Sorry. Oh, so we'll come to. We'll see how to do that later on. How do you know that Q bar over K has infinite degree? And the next question is Q bar countable? Anderson's theorem says yes, Q bar is a countable field. R is uncountable. So how about finite extensions? So finite extensions are characterized by the following theorem. Suppose L over K is an extension and the following conditions are equivalent. First one, if L over K is finite, 2, L over K is algebraic, and L is finitely generated over K. Three, so there exists finitely many algebraic elements alpha 1 up to alpha n of L such that L is equal to K of alpha 1 up to alpha n. So this is how you characterize finite extensions, any finite extension. So any finite extension can be written as L of K of alpha up to alpha n for some alpha and for some n for K. So this is the basic import of this theorem. If suppose the first condition L over K is finite, and suppose alpha belongs to N. So we want to show that L over K is algebraic. So suppose alpha belongs to N. And therefore, if you consider the extension K of alpha over K, so this is sitting inside L like this. So this is finite, and therefore this is also finite by the Tower law. So, but if this is finite, it follows that alpha is algebraic over K by the previous fundamental theorem. This is important theorem. Okay. So L over K. So since alpha is a general element, it follows that every element of L over K is algebraic, and therefore the extension L over K is algebraic. So that is the first part of the second point. Now you have to show that L is finitely generated over K. Okay. Consider L as a vector space over K. Then there exists, since L over K is finite, there exists elements beta 1 up to beta r. This is a basis of L over K. So in particular, L is a unique, L can be written as a linear combination of K beta 2 plus K beta r. That is the definition of a basis. So K, in particular, L is generated by beta 1, beta 2, beta r. I forgot what I mean by finitely generated. So a field is said to be finitely generated over K. Let us suppose L is finitely generated over K. If you are able to find a surjective homomorphism K from K bracket x1 to xn to N. So this is surjective homomorphism. you can do that, then that field L is said to be finitely generated over K. So here, if you send, so you can easily see, because L is, so beta 1 up to beta R is a basis of L over K. In particular, if you can send x1 to beta 1, x2 to beta 2, and xn to beta n, okay, and then you can see that because L has basis beta 1, beta 2, beta n, follows that this is a surging to homomorphism, and therefore L is finitely generated over K. So this is the point. Now 2 implies 3 is trivial, because if L is algebraic and so L is finitely generated over K means there exists these finitely many elements beta 1 up to beta n. Each of them are algebraic because L over K is algebraic, such that L is equal to K of alpha 1 up to alpha n, which is precisely what this means. Okay, so that 2 implies 3 is trivial. So now you have to show that 3 implies 1. So let K naught is equal to K, and K1 is equal to K of alpha 1. Okay, so let us take this alpha 1 up to alpha n elements of L such that L is equal to this. So we consider this as a tower is equal to Kn. This is Kn minus 1 is equal to K of alpha n minus 1. So Kn minus 2 is equal to K of alpha 1, alpha n minus 2. So K1, which is K of alpha 1 over K. Now you see, so each alpha 1 is algebraic over K, so this is finite. And now we have K2, which is equal to K of K1 of alpha 2, which is K of alpha 1, alpha 2. So alpha 2 is algebraic, already algebraic over K. In particular, it is algebraic over K1. And therefore, this degree is also finite. So by induction, you can see all these degrees are finite. And therefore, by the tower law, this is also finite, which is precisely what we need to show. So this theorem is actually an extension of our previous theorem, which actually characterizes algebraic elements. So alpha is alpha belonging to L is algebraic if K of alpha over K is finite. So that was the previous theorem, and based on this theorem, we show that the whole extension L over K is algebraic. L over K is finite if and only if L is equal to K of alpha 1 up to alpha n. So this is how you characterize finite extensions. So this is a trivial consequence of this basic theorem. Okay. Now corollary to corollary. L over K be an extension and S be a subset of L. And if each alpha belonging to S is algebraic over K, then K of S over K is also algebraic. Why? Why is this algebraic? So S may not be finite. Now, S may not, so in order to show that K of S over K is algebraic, what do you need to show? Pick an element in K of S and show that so beta would be what? Beta would belong to K of alpha 1 up to alpha n for some alpha 1 up to alpha n. Because beta, if you recall how this is constructed, beta is of the form f of is a polynomial in the finite products of these elements. So quotient of two polynomials, where each polynomial is a linear combination, a k-linear combination of products of these elements. So there exists some, so if you consider all those elements which appear in this expression of beta, it follows that beta, there exists alpha 1 up to alpha n, such that beta belongs to this. And each alpha I is algebraic. Because each element of S is algebraic over K by hypothesis. Now, if this whole thing is algebraic, and therefore beta belongs to this algebraic extension, and therefore beta is also algebraic. Now, why is this algebraic? Because if you consider this L by the previous theorem, so if L is equal to K of alpha 1 up to alpha n, where each alpha 1 and alpha n are algebraic, it follows that L over K is finite, therefore L is a finite extension. L is an algebraic extension. Okay. Okay. So this is a thing, and finally we have a following theorem. So if M is algebraic over L and L is algebraic over K, and then M is algebraic over K. So previously we assumed that these are finite, but here we don't need that. We just need to show that M over K is algebraic. So all you need to show is if alpha is an element of M, you want to show that K, alpha is algebraic over K. But since alpha is, so if alpha belonging to M, then alpha is algebraic over L. And therefore, there exists some minimal polynomial M alpha, which is of the form L0 plus L1x plus Ln(xn) is the minimal polynomial of alpha, where Ln is equal to 1. Okay. So then, okay, let's put it as 1. It doesn't matter, just for the sake of proper pieces. Then this implies alpha is algebraic over K of L0 up to Ln, because alpha satisfies a polynomial with coefficients in this field, and we have exhibited one particular polynomial. So note that this one may not, yeah, okay. It's interesting. Okay. So alpha is a minimal polynomial. So alpha is algebraic over this, and therefore K of L0 plus Ln alpha over K of L0, and so this extension is finite. Okay. Now, since each L0 belongs to L, and you know that L over K is also algebraic, and therefore, by the previous theorem just we discussed, if you consider the extension, if you consider this extension is finitely generated by L0 up to Ln, and each of the elements L0 up to Ln is algebraic, and therefore by the previous theorem, this is algebraic, and therefore this is finite. This was already shown to be finite because it has degree at most n, and therefore the whole thing is finite. And by the previous, by the fundamental theorem, it follows that alpha is algebraic over K. Okay. So algebraicity has a certain kind of finiteness embedded into it. And finally, there is one simple theorem which is which you can see. Theorem. Suppose L is L over K is an extension, and tau is an injective map which fixes K. I.e., tau of little k is equal to little k for each little k into k. It fixes K. And suppose tau is an injective map. The main hypothesis is the extension is algebraic. If that were the case, it is called monomorphism. just like homomorphism. Mono means one is a monomorphism, and tau is injective, and tau fixes k, then tau is surjective. And therefore, tau is in fact an automorphism of L, which fixing k. So this is the notation for automorphism of L fixing k. So how do you show that tau is a surjective? So in order to do that, pick. So certainly tau is a ring homomorphism. Therefore, tau of 0 is equal to 0. Suppose alpha is a non-zero element of L, and let m sub alpha is the minimal polynomial of alpha over k. And let R be the set of roots of m alpha in L. I'm not saying that all the roots of m alpha are present in L. I'm just saying that all the roots of m alpha which are present in L. That's all. There may be, so, but I know that the set of all the roots consists at least alpha, because alpha belongs to L. And then we took the minimal polynomial of m alpha. And now suppose beta is another root of R, which may be equal to alpha, but that doesn't matter. Now m alpha of tau of beta. So I'm saying tau of beta is tau of m alpha of beta. This is where you have to see. Suppose k naught plus k1x plus kn x to the power of n is the minimal polynomial of alpha. Now, if you apply tau to this, this becomes, if you take k naught plus k1 tau of x, let us say this is beta. Tau of beta plus kn tau of beta to the power of n. So why? Because tau fixes k, and therefore each of these elements are sent to itself. And tau of, because tau is a ring homomorphism, tau of beta to the power of k is equal to tau of beta to the power of k. Therefore, you see this is of the form ki tau of beta to the power of I. So which is m alpha substituted by tau of beta. So tau of m alpha beta is equal to m alpha of tau of beta. But beta is a root of the minimal polynomial. And therefore, tau of 0, which is equal to 0. In other words, tau of beta must, from this it follows that m alpha of tau of beta is also equal to 0. That means tau of beta must be sent to some root of R. Okay. Now, you already know that so far we haven't used the fact that tau is 1 to 1. Now we know that tau is 1 to 1. And R is a finite set because the number of roots of minimal polynomial is finite. So if you have R, so each root in here of the minimal polynomial of alpha is sent to another root of m alpha. So R is finite and the tau is injective, and therefore this must be surjective. Okay. So in particular, since each and every element of L can be realized as the root of some minimal polynomial of that over k, you see that this thing is hit by some element in here, just like this. That is to say, tau is surjective. So this finishes off some basic properties of algebraic extensions. So next class we will look into some other properties, especially improve some problems from Greek antiquity. All right.